I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about ruby laser. In our previous lectures, we have seen the introduction to laser. We have also seen some important phenomena, that is stimulated absorption, spontaneous emission and stimulated emission. We have also defined some terms: metastable state, population inversion and lasing action. Today, with the help of all these things, we are going to do ruby laser. Now, the brief outline of today's topic. First, for our understanding, to understand ruby laser, we will quickly revise what we have seen in the basic terms that are involved in laser. And then we will also understand the lasing action and the laser system, and then apply the same to the ruby laser setup and see the working of ruby laser, and also study the energy level diagram of ruby laser. And finally, we will discuss the applications of ruby laser. First, the term laser, which originated as an acronym, is for light amplification by stimulated emission of radiation. So whenever we say laser, so immediately we understand that it is light amplification by stimulated emission of radiation. Now, what are the characteristics that makes the laser light very special is high monochromaticity. High monochromaticity means mono is related to single, chromaticity is related to color. So, light of single wavelength. So, laser light means it is a light of almost single wavelength. Then it has high degree of coherence. Coherence here means same phase. They have the same state of vibration. So we say it has got high degree of coherence. Then high directionality, or we may also say it is unidirectional. It is unidirectional means if you see ordinary light, when light is emitted from an ordinary light source, it is spread in all the directions. But when we see a laser light, it will emit only in one direction. Means even if the light travels a few lakhs of kilometers, it will diverge only for a few centimeters. That makes it so special and has got lot of applications due to it. Then comes the high brightness. Brightness is always related to intensity. That is, the amount of light that is emitted per unit area per unit time is more. So that is why it is very bright. Now the first phenomenon we have seen is stimulated absorption. So in stimulated absorption, what we see is we have a ground state whose energy is E1. This is the ground state. And then we have an excited state whose energy is E2. So the energy of the ground state is represented by E1 and the energy of the excited state is represented by E2. And when you see, the atoms are generally in the ground state. So the atom is in the ground state whose energy is E1, which is less when compared to E2. Now, if this atom has to go or make a transition to the excited state, we need to supply energy. So, how do we supply energy? We supply it in the form of a photon given by E is equal to h nu, and this 1, 2 represents a minimum of energy which is equal to the difference in the energy levels E2 minus E1 has to be supplied. Only then this atom can make a transition to the excited state. So the atom now goes to the excited state with the help of this photon. So what we see here in the definition is, if a photon of energy h nu 12 means this represents the difference in energy collides with an atom which is present in the ground state of energy E1, then the atom completely absorbs the incident photon and makes transition to the excited state. So this is what we have seen in the phenomenon here. The atom is in the ground state, a photon is incident whose energy is at least minimum equal to the difference in energy. So when this collides with the atom, this will completely absorb the energy and then it will make a transition to the excited state. So this process we are calling it as stimulated absorption. Now coming to spontaneous emission. So in spontaneous emission, what we see here is we have the atom now in the excited state. Where is the atom now? It is in excited state whose energy is E2. So this is the excited state and this is the ground state. So the atom which is initially present in the excited state makes transition voluntarily on its own without the aid of an external stimulus to the ground state and emits a photon of energy E2 minus E1. So what we see here is the atom which is in the excited state here having energy E2 without any stimulus on its own, it is coming to the ground state. How it is coming to the ground state? Now, this is energy E2. It is having more energy here. Now it is coming, it is making a transition to the lower energy level. So the difference in energy E2 minus E1 is being emitted. So this emission, this process of emission, we call it as spontaneous emission. We need to understand why this atom comes to the ground state. Because when we excited it to the excited state, this atom cannot stay in the excited state for a longer time. It can stay only for a time which we call it as the lifetime. The period for which the atom can stay in the excited state, we are calling it as lifetime. Once the lifetime is over, the atom has to make a transition to the ground state. So it comes to the ground state by emitting the energy, that is the difference in energy E2 minus E1 is being emitted, and we call it as spontaneous emission. Now coming to stimulated emission. So why do we have to go for stimulated emission? In spontaneous emission, whatever energy is being emitted, it is going waste because the difference in energy is most of the times non-radiative. We do not get any laser from that. Now, if the photon is in the excited state E2 and when the atom is still in the excited state, if you can stimulate it with the help of an external photon. So, the atom is here. This is the incident photon whose energy is given by E is equal to h nu 12. Because of this stimulation, what happens? The atom will come down to the ground state. So when it comes down, what happens? The difference in energies is being emitted, and also whatever energy we have supplied, that is also being emitted. So we have E is equal to h nu 21. This is the emitted energy and this is the incident photon. Now, if you see these two, they are in phase with each other. So you get a coherent beam, which is laser beam. So with the help of stimulated emission, we can achieve a laser or a coherent beam. So a photon having energy impinges on an atom present in the excited state. So this photon is incident on the atom that is present in the excited state. Then what happens? The atom is stimulated to make a transition. This atom is stimulated with the help of this photon. For what? To make a stimulation to the ground state. So this gives off a photon of energy h nu to 1. So this is the, when it is coming to the ground state, it is giving off energy is equal to h nu to 1. And also there is an incident photon. And these two are coherent. They are in the same phase. So we are calling it as stimulated emission. Now we have also seen the terms involved. Lifetime, the time for which the atoms can stay in an excited state, we call them as lifetime. And we also have seen a metastable state. What is a metastable state? It is an excited state in which the atoms can stay for a relatively longer time. In an excited state, it may stay for a very less time, but if you have some state in between where the atoms can stay for a relatively longer time, it will be very useful for stimulated emission. Now coming to lasing action. So in lasing action, there are 3 steps that are involved. So the first step is pumping. The second step is population inversion. And the third step is the stimulated emission of radiation. Any laser we take, what we need to understand is what is the basic lasing action. And the second one is what is the laser system. What is the laser mechanism that is happening. So first we will try to understand these 3 steps and then go to discuss in detail about the ruby laser. So in pumping, what is happening? It is the process of sending the atoms from lower energy level to higher energy level. So the atoms which are present in E1, that is the ground state, if we have to send them to excited state, we need to supply energy. And this process of sending the atoms from lower energy level to higher energy level by supplying energy, we are calling it as pumping. And there are different pumping mechanisms. And we use different pumping mechanisms for different types of lasers. So, for example, for ruby laser, which we are going to discuss, we will use optical pumping. Optical pumping here means we'll be using light as a energy source. So, using that energy, the atoms will make a transition into the excited state. So, pumping can be achieved using an energy source, and the energy source we will use here is the optical pumping. And when it comes to helium neon laser, the pumping mechanism is electric discharge. There will be a discharge because of the high voltage that we are supplying between the ends of the cavity. What happens is there will be an electrical discharge, and because of that the atoms will gain the energy and then they go to the excited state. And in semiconductor laser we use direct conversion, and in CO2 laser we use chemical reaction. These are the different pumping mechanisms we use for different lasers. Next comes the population inversion. Population inversion can be achieved easily with the presence of a metastable state. So first we will have to understand population, then we will see what is population inversion and how it can be achieved with the help of a metastable state. This is one thing which we have to be very clear about to understand laser. So population always represents the number of atoms that are present in a given state. First, I will show 2 levels. E1, the ground state, energy of the ground state. E2 is the excited state. So this is excited state. And this is ground state. Generally, when you see, the atoms are always in the ground state. And the number of atoms in the ground state are represented by N1. N1 represents the number of atoms in the ground state, which we also call it as population. If you see in the excited state, the number of atoms will be less and you may represent it as N2. N2 is the number of atoms in the excited state and N1 is the number of atoms in the ground state. And if you see the condition here, N1 is less than N2. N1 is less than N2. But if this is the condition, we cannot go for stimulated emission or we may not get laser. To get laser, the number of atoms in the excited state should be more than that in the ground state. So for that, what we do pumping. So we have discussed that pumping is the process of sending the atoms from ground state to excited state. So by some pumping mechanism, we send the atoms which are there in the ground state to the excited state. So after pumping, what happens? The number of atoms in the excited state will be more than the number of atoms in the ground state. So N2 will be greater than N1, which we are calling it as population inversion. Why we are calling inversion? The general condition is N1 should be greater than N2. N1 should be greater than N2 is the general condition. Now N2 is greater than N1 means we are just reversing it. So we are calling it as population inversion. So what we are seeing here in population inversion is the number of atoms in the excited state is more than that in the ground state. Now what happens here after pumping, if the atoms are more here, they cannot stay there for a longer time. So they make the transition. Before we do anything, they come to the ground state and there may be non-radiative emissions. Then if you have another state in between where the lifetime is comparatively more than E2. Okay. If we say the energy here is E3, if they make a transition to this state, which we call it as metastable state. So in metastable state, what is happening? The atoms can stay for a relatively longer time. And because they stay for a relatively longer time, we get the time to stimulate them and bring them down. So in population inversion, it can be achieved with the help of a metastable state. So what happens here? Even after making transition to the metastable state, this condition N2 greater than N1 still holds good because the number of atoms in E3 will be more than that in E1. Even after they make a transition from E2 to E3. So population inversion can be very easily achieved with the help of a metastable state. If this state is not there, then it becomes very difficult. Then we have stimulated emission of radiation. The photons that are produced by stimulated emission means we are stimulating them with the help of an external photon to make the transition to the ground state. And when they are in phase, the incident photon and the emitted photons, when they are in phase, they produce coherent light, which we call it as laser. Now we see the lasing action where all the three steps are being followed. Even the ground energy of the ground state. So this is the incident photon. This is what we are calling as pumping. We are pumping the atoms from the ground state to the excited state. The energy in the excited state is E2. Now you can see that the number of atoms in the excited state is more than the number of atoms in the ground state. Means this is the condition where population inversion has occurred. So when there is population inversion, with the help of a stimulation, external stimulus, we can get them transition to the ground state and we get laser. So photons produced by stimulated emission will have a definite phase relationship which gives rise to coherent light. Now coming to the laser system, it consists of three basic parts. The first one is the active medium. What is an active medium? It is a set of energy levels to support laser action. So if you need laser action, you need to have a different energy levels which we have discussed now. The ground state, the excited state and the metastable state. You may have more number of levels also. Till now we have discussed only 2 level and 3 levels. So a suitable set of energy levels are very much required for laser action, and active medium is a part of it. Then we have the energy source. Energy source is a source for pumping. So why we need an energy source? We need population inversion. Why we need population inversion? Only when there is population inversion, we get transition to the lower level, energy will be emitted, and if it is coherent, we get laser. So energy source is very much required. That is the source of pumping to attain population inversion. So the second part is the energy source. And the third one is an optical cavity or a resonator. An optical cavity is required to introduce optical feedback so that we maintain the gain system, overcoming all the losses. During the process of this pumping, some amount of energy may be lost. But even after that, when you have an optical system where there is an optical feedback and due to multiple collisions and reflections, the energy will be supplied in a continuous manner. So when this optical feedback is provided with the help of dielectric mirrors or polished coated ends, okay, we will be able to achieve the laser. Now this is the basic diagram, or I can say it's a block diagram for laser system, where you have the laser medium. We are taking the laser medium. The next one, this is one. And the second one is the pumping mechanism. Whatever mechanism we choose depending upon the laser. The second is the pumping mechanism. And the third one is the optical resonator cavity. All this is an optical resonating cavity, which will have mirrors at both the ends. This is the rear mirror with 100% reflection, and this is the front mirror with 95% reflection, from where we get the output laser beam. So any laser we discuss will have these three basic parts: the laser medium 1, then the pumping system 2, and then the optical resonating cavity 3. Now in laser, ruby laser, if we discuss, what is the active medium? So the first thing we have seen is the active medium. So in ruby laser, a single crystal of ruby in the form of a cylinder acts as the laser medium. So we need to identify what are these three things in a ruby laser. So the first thing is an active medium, a crystal of ruby. It may be a cylindrical rod of ruby. What is ruby crystal here? It is a composition of aluminum oxide doped with chromium atoms. So this forms the active medium. So here the active medium is made up of a host of sapphire, we are calling aluminum oxide, which is doped with small amounts of chromium ions. And this ruby has good thermal properties. Means they can transmit the heat or the energy very easily. Now the second thing is the energy source. What is the energy source we are using here in ruby laser? So we use a flash tube as the energy source or a pump source. This flash tube supplies the energy to the laser beam. This flash tube will be filled with gas like argon or krypton, and this will be supplying the energy to the laser medium. So once you have the active medium or the laser medium, then you need energy to pump the atoms to the higher level. So what we are using here is the flash tube. So when lower energy state electrons in the laser medium gain sufficient energy from the flash tube, they jump into the higher energy state or the excited state. So what is happening? The atoms that are there in the active medium, with the help of the energy we are supplying, they are able to gain the energy and they are able to make a transition from lower energy level to higher energy level. The third one is the optical resonator. So what is the optical resonator here? The ends of the cylindrical ruby rod are flat and parallel. The active medium, I said, we are taking a cylindrical ruby rod. Both the ends of the ruby rod are flat and parallel, and the ruby rod is placed between two mirrors for optical feedback. The optical coating is applied to both the mirrors. When you place two mirrors at the two ends of the ruby rod and they are coated, optical coating is done. What is that coating? The process of depositing thin layers of metals on glass substrates to make mirror surfaces is called silvering. When we discuss about ruby rod, we will talk about silvering. What is the silvering? Either polishing it or depositing thin layers of glass substrates. Because of that, what happens? They will be reflecting. So this is what we are calling it as silvering. And each mirror, we are placing two mirrors at the two ends. Both of them are coated, but they are coated differently. Okay. One may be coated 100%, and the other may be 95 to 98%. What is the purpose? We are going to see. So the ruby rod is having two mirrors at the two ends, and there is an optical coating. With the help of glass substrates, we are doing some deposit and we are calling it as silvering, and each mirror is coated differently, means the percentage of coating may be different. Now at one end of the rod, the mirror is fully silvered, whereas the other end is partially silvered. One end is fully silvered, means 100% polished or 100% coated, and the other one is partially. Why? What is the reason for that? The fully silvered mirror will completely reflect the light, whereas partially silvered mirror will reflect most part, but it will allow small portion of the light to produce output laser. So that is what we need to understand. When we are coating both the mirrors, one is 100%, where we have coated 100%, it will be reflecting all the light, and where it is partially coated, it will allow some light to come out through it, where we get the laser output. Now, ruby laser is the first type of laser that is demonstrated in the year 1960 by the scientist Wyman. And it is a solid state laser. When we were discussed different types of laser, we have seen we have gas lasers, we have solid lasers, we have chemical lasers. Here we are discussing about the solid laser. Ruby laser is a pulsed 3-level pumping scheme. So what is this pulsed laser and what is this 3-level laser, we are going to discuss. But what you need to understand is, whatever pumping we are doing, it is not continuous. It is given in the form of pulses. That is why we are calling ruby laser is a pulsed 3-level pumping scheme. So we will be seeing 3 levels, and also we will be seeing the pumping in pulses. And the active medium here is aluminum oxide combined or doped with chromium oxide. And active is the chromium ions. The energy levels of chromium will help us in getting the lasing action. Now, how we are doing that doping is, some of the aluminum atoms are replaced by 0.05% of chromium atoms. We are replacing the aluminum atoms with chromium atoms, so that the lasing action can take place in chromium energy levels. And the energy source we are using here is optical pumping using a xenon lamp. So I told we are taking a tube, a flash tube, in which we will be filling the gas. So we are calling it as a xenon lamp. Now let us see the construction. So in ruby laser, what we see is a cylindrical shaped ruby crystal rod. So if you see in the figure here, this is the rod we are seeing. You can see this pink colored one. This is the rod. Cylindrical rod. One end of the faces is highly silvered. So if you see here, this face is highly silvered, 100% reflective, because It is highly silvered, it is 100% reflective, and the other phase is partially silvered. Means which is the other phase? This is the other phase. It is partially silvered, so it is only reflecting 95%. So why we are doing this partial silvering is, it will transmit 10 to 25%. If it is 90%, it may transmit 10% of the incident light and reflects the rest. So here you can see the output here. The laser beam output you can see from the partially silvered phase. Now this ruby crystal is placed along the axis of a helical xenon or krypton flash lamp of high intensity, and this is surrounded by a reflector also. Now if you see, what is this helical xenon lamp? This is the helical lamp. If you can see, this is what we call it as helical, a spring type. No, we say this is helical. So this is the flash lamp. Helical xenon means the tube, the flash tube, which is filled with xenon or krypton gas with high intensity. So now this is the source, the energy source here is the flash lamp. How we are placing the ruby rod along the axis? If you are taking the helical lamp, xenon lamp, we are placing the ruby rod along the axis of the xenon flash lamp. This is how we place, so that the rod will be surrounded by this flash lamp. And also we have a reflector. So where is the reflector? Why we are using this reflector here is, whatever light that is emitted will reflect back onto the rod and not be lost to the surroundings. Now the ends of the flash lamp are connected to a pulsed high voltage source. If you see here, this is the end, one end, and this is the other end. So to this, what we are connecting? A high voltage supply. And this high voltage is a pulsed one, means you will get flashes of light. Once you switch it on, the energy will be supplied in flash. Once it glows, there will be energy that is emitted and the ruby rod will absorb the energy. So the lamp will give flashes of intense light. It is not continuous. It is just emitting flashes, and this flash will be only for a few milliseconds. So within that time, the ruby rod has to absorb the energy for the atoms to gain energy and get excited to the excited state. Now this ruby rod is protected from heat by enclosing it in a hollow tube through which cold water is circulated. So when we see here, this lamp, when it is emitting pulses or giving out flashes for a few milliseconds, but very high amount of energy is being emitted. But out of that, only a part of it is being absorbed by the rod and remaining it is emitted out. So because of that, lot of heat is generated surrounding this ruby rod or the lamp. And in order to cool it, what we are doing it, we are enclosing it in a hollow tube through which cold water is being circulated. Otherwise, the entire system gets heated up. When the flashes are coming out, that means the energy is being emitted. The ruby rod absorbs some of the energy, some of it is transmitted, which creates lot of heat. And to cool it, we are using a tube, a hollow tube through which cold water is circulated. There will be an inlet for the water. Cold water comes in. When it gets heated up, it passes out. So there will be a continuous flow of cold water which keeps the system cool. Then coming to working. So we will see in general with respect to E1, E2 and E3, and then we will also discuss in specific what will be the levels for ruby. So a ruby laser medium consists of 3 energy levels, E1, E2 and E3, because we have seen it's a pulsed level laser system and 3 level laser. So what are the 3 levels here? E1, E2, E3 with n number of electrons. And how are the energy levels? E1 is less than E2 less than E3. Means E1 is the ground state, E2 will be metastable and E3 will be the excited state. So this is how the energy levels are. Energy level E1 is known as the ground state, E2 is known as the metastable state, and E3 is known as the pump state or excited state. Now, initially, most of the electrons are in the lower energy state E1. If you see in the first figure here, we focus on first one. All the electrons, most of the electrons are in E1, which is the ground state. And we have very few in E2, the metastable state, and E3, the excited state. So, most of them are in the ground state. Now, what we are going to do, we are going to supply energy. We are going to excite them. Because of the absorption of energy, what is happening here? There is pumping. What is happening here? Pumping. Pumping means excitation of atoms from lower level to higher level. So, what is the condition we are achieving? Population inversion. The number of atoms in N3 is greater than N1. So, the population inversion is achieved. But what happens here in E3? They cannot stay for a longer time. So, what happens is they emit radiation and they come to the E2. That is the metastable state. There is a transition from E3 to E2. Now, what is the importance of this metastable state is, even after the atoms have come to the lower level, still this condition of population inversion is achieved. N2 greater than N1. So, this is what we are calling as population inversion. So, once the population inversion is achieved, you can stimulate them and bring them down, getting laser. So, when light energy is supplied to the laser medium, that is ruby, electrons in the lower energy state gain energy and jump to the state E3, excited state E3. But the lifetime of the pump state is very small. Pump state or excited state both mean the same here. What is the lifetime? 10 power minus 8 seconds. So, the electrons do not stay there for a longer time. They cannot stay there for a longer time. After a short period, they will just fall down to the metastable state E2 by releasing the energy. Okay. So, what happens now is all the atoms that are there in the excited state, after the lifetime is over, they have come to the metastable state. And the lifetime of the metastable state is 10 power minus 3, which is much greater than the lifetime of E3. If we see the lifetime of E3, it was only 10 power minus 8 seconds. But now they can stay for 10 power minus 3 seconds in metastable state. So, therefore, electrons reach E2 much faster than they leave E2. So, immediately from excited state, they are coming to metastable state, but they are staying there for a longer time. And because of that, what happens? It results in an increase in number of electrons in the metastable state and population inversion is achieved. So, why we are discussing all this is to achieve population inversion. So, after some time, what happens? The electrons in the metastable state E2, they fall to the lower energy level E1 by releasing energy in the form of photons. So, naturally, when they come from E2 to E1, the difference in energy is being emitted in the form of photons, and we call it as spontaneous emission. But what happens when these emitted photons interact again with the electrons in the metastable state? They will forcefully make the electrons fall to the ground state. This is very important because in spontaneous emission, we may not get any useful radiation. But when these atoms again, they will interact with the atoms in the metastable state and they will make them forcefully fall to the ground state. And because of which what happens? Two photons are emitted. The one which is incident and the one which is making transition. Two photons are emitted. and we call this as stimulated emission because it is not happening naturally. It is because of the stimulation by the emitted photons. So we are calling it as stimulated emission. Now when these emitted photons again interact with the metastable atoms, 4 photons are produced. So first we had one which is interacting, because of that we had 2. Now these 2 will interact with the 2 more. So like that the chain reaction will start. So now how many we are having? We are having 4 photons. And because of this, the continuous interaction with the electrons, millions of photons are produced. So these 2 will go now and they will collide with 2 more. So like that they keep on multiplying and millions of photons are being produced. So in an active medium, Ruby, a process called spontaneous emission first produces the light, and the light that is produced within the laser will bounce back and forth between the 2 mirrors. So we are discussing about the interaction of the emitted photons, and this stimulates the electrons to fall to the ground state by releasing light energy, which is called stimulated emission. And millions of electrons are stimulated to emit light, and then light gain is achieved. And this amplified light will escape through the partially reflecting mirror to produce the laser light. So the entire phenomenon what we are seeing in general we have discussed. Now if you see the working exactly for a ruby laser, the chromium ions are responsible. So if we are talking about the active medium, what is the active medium here? Chromium ions. They are responsible for stimulated emission of radiation. And what about the aluminium and oxygen ions? They are passive. They are only sustaining the lasing action. Means lasing action here means what? We have seen 3 steps in lasing action. The pumping, the achievement of population inversion, and then stimulated emission. So these are only helping in doing that lasing action, but the chromium ions are actually responsible. So what is happening here is, so this is the ground state for chromium atoms. Now they absorb the radiations of wavelength 5500, which is represented by green, and 4000, that is blue, emitted by the flash lamp, and they get excited to 4F2 and 4F1 energy levels. Till now we were talking in general E1, E2, but now specific for Ruby, what are the energy levels we are mentioning here is 4F2 and 4F1. The atoms which are in the ground state, once the flash occurs because of the xenon flash lamp, they absorb the energy. Which energy they are absorbing? Corresponding to the wavelengths 5500 and 4000. They are absorbing this energy and they are making transition to 4F2 and 4F1 from the ground state. Now after the lifetime, these ions make non-radiative transition to the metastable state 2E, consisting of a pair of energy levels. So here these are the excited states now. 4F2 and 4F1 are the excited states in Ruby. Now they cannot stay here for a longer time. They can stay only for a lifetime, and once the lifetime is over, they have to make transition to the lower level. So now when they are making the transition to the lower level, it is non-radiative transition. So maybe thermal energy is being emitted. So they are non-radiative. And where they are going to the metastable state 2A, which has got a doublet. So you can see 2 levels. Doublet means here 2 levels which are placed very closely. So population inversion takes place between metastable and ground state. Now these atoms which are now in the metastable state, still N2 is greater than N1. So the population inversion has achieved. And because of this, there is emission. When these atoms come from the metastable state to the ground state, there may be 2 types of radiations. One corresponding to the wavelength 6929 and the other one is 6943. Out of which 6943 is the laser radiation of high intensity. So two types of wavelengths we are getting. Mostly 6943 is of high intensity. So what are the advantages of this laser? It has a very large power output, and the pumping efficiencies can be increased by using the mirrors, and it has a very narrow line width. Very narrow means it is highly focused. Then what are the drawbacks of this ruby laser? It is a 3-level pumping scheme which requires very high pumping power. When you have to pump them from ground state to higher level, you need to have a very high pumping power, because when we are supplying the energy has to be the difference between 3 and 1. Now that much energy we need to supply. So we need a high pumping power. And laser output is not continuous. We have seen it is only in a pulsed mode. Only when there are flashes of light, the ruby rod is able to absorb the energy. So it is not continuous. It is only a pulsed laser. It is in pulsed mode. Then efficiency is very less, because only green and blue components of the incident light are being absorbed and the remaining are left unused. When we have seen the energy level diagram, we have seen that radiation or the wavelengths of green and blue are being absorbed. So when only these two are absorbed, the remaining are left out. So the efficiency is very less. That is also one drawback of ruby laser. Now coming to applications, ruby laser is used in distance measurement using pulse echo technique. So you can measure the distance using pulse echo. Suppose I want to measure the distance from point A to point B. I will send a laser pulse from the point A. So this is the pulse that goes, and we will receive an echo after that. So you know the distance between A and B by calculating the time the pulse reaches here and comes back for the pulse and echo. And you know the speed with which it is sent. We know velocity is equal to distance upon time. So the distance can be measured by knowing the velocity and the time taken for the pulse. That is what we are calling as pulse echo technique. Then ruby laser is also used to create holograms of large objects such as aircraft tires to look for weaknesses in the lining, because these aircraft tires have to be checked periodically. So in order to check them, what we do here is to create a hologram of these large objects, so that if there is any minute weakness in the tire, that can be detected. It can also be used in atmospheric ranging, scattering studies, and also LIDAR measurements. Here, LIDAR represents light amplification and ranging. It is also used for trimming resistors and integrated circuit masks. So wherever you have to trim the resistors, when we are using resistances in circuits, or we use ICs, there also when we used to trim them, we can use this ruby laser. So they are also used in research, and they are used in research applications such as plasma production and fluorescence spectroscopy. Spectroscopy is generally used to study the structure of atoms, so it is also used in scientific purposes. And one of the main industrial uses is to drill holes in diamond, because it is very precise. You can make precise holes in diamonds because it is very focused and unidirectional. So the greatest industrial use is to drill holes in diamond. And it is also used in military as target designators and range finders. Range means the distance between the point at which you are sending and the receiver. Ruby lasers are extensively used in tattoos and hair removal. So this is one general applications which we see in our day-to-day life. With this, I conclude my session. See you in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.